In this video, we're going to continue talking about the ideal gas law and look at some of the applications of the ideal gas law. But to start with, we're just going to talk about some definitions. The first one is molar volume, and that's the volume occupied by 1 mole of a substance. And remember, in this, we're talking about gases here. We also have something that's called STP, or standard temperature and pressure. And for us, as chemists, STP means 273 Kelvin in 1 atmosphere. Now, since we have a standard temperature and a standard pressure, and let's say we're working with 1 mole of substance, we can calculate a standard volume using the ideal gas law. So remember, the ideal gas law is PV equals nRT. So all we did here was we moved the P over to solve for V. So we have 1 mole of stuff multiplied by the gas constant, multiplied by our standard temperature, divided by our standard pressure, and we get 22.4 liters. So no matter what type of gas you're working with, at standard temperature and pressure, 1 mole of that gas will always take up 22.4 liters. So here's a question for you. So let's assume we're working with ideal gases. Which of these gas samples has the greatest volume at STP? 1 gram of hydrogen gas, 1 gram of oxygen gas, or 1 gram of argon gas? Pause the video, see if you can figure this one out. Come back when you have an answer. Alright, let's take a look at this. So what we want to do is we want to convert all these grams to moles so we can use the ideal gas law, calculate volume. So I'm going to start that with hydrogen. The molar mass of hydrogen is 2.02 grams per 1 mole. So with 1 gram of hydrogen, we have 0.495 moles of hydrogen. I'm going to do the same for oxygen and have 0.0625 moles of oxygen. Same for argon, and I have 0.0250 moles of argon. Now for our moles, we have to calculate what the volume is. So for hydrogen, I'm going to use PV equals nRT. I have all the values listed in here already, solving for V. So with 0.495 moles of hydrogen, we have 11.1 liters. For oxygen, with 0.0625 moles of oxygen, we have 1.40 liters. And with argon, with 0.025 moles, we have 0.560 liters. So the gas that takes up the greatest amount of volume would be hydrogen. Alright, so let's talk about density of gases. We talked about densities of solids and liquids, and density for gas is a little different because density here is molar mass divided by molar volume. And at STP, we're going to assume the molar volume is 22.4 liters, as we talked about in the previous slide. So let's look at the density of helium versus nitrogen. So helium, our molar mass is 4 grams. So we take up 0.179 grams for every liter of helium gas. While nitrogen, it's heavier, so we have a weight of 1.25 grams per every liter. So that is just how you use density of gases. It's molar mass divided by a molar volume. So anything less dense than air will float, and that is why we can get air balloons, because the gas inside of there, such as helium, which is 0.179, will float above nitrogen, which makes up roughly 80% of the atmosphere. That is why helium balloons float. They are less dense. Now let's see if we can use this concept. So let's say we have a sample of gas that is 827 milligrams. This gas takes up a volume of 0.270 liters at 88 degrees centigrade. And at that temperature and volume, our pressure is 975 millimeters mercury, or torr. With all that information, can you find the molar mass? And here's the gas constant. Here's how we convert from atmospheres to torrs. And remember, molar mass is mass divided by moles. You're also going to want to use the ideal gas law here. So pause the video, try to figure it out, come back when you have an answer. Alright, let's take a look. So the first thing we're going to do, we're going to convert this torr into atmospheres because our gas constant is in atmospheres as well. So we do that, and as you see, we are working with 1.28 atmospheres. We got to convert our temperature from Celsius to Kelvin because our gas constant's in Kelvin. We can then use the ideal gas law. So PV equals nRT. We want to solve for the number of moles we have because we want to find the molar mass. We have a mass, but we don't have moles. So I'm going to plug in pressure, volume, gas constant, and temperature, and see we're working with 0.0119 mole. Now I can solve for molar mass. So remember, molar mass is grams divided by moles. That's the units we're used to. So it's 0.827 grams. We don't want to put 827 milligrams there. We want to convert to grams. Divided by 0.0119 moles, and we get our molar mass as 95.5 grams per mole. And that's it for this video. See you in the next.